2001, il fait des études à Tecnológico de Monterrey en Mexique. Donc, c'est pas allumé le. Donc, si c'est pas bien enregistré, je suis désolé. Alors, voilà, je passe la parole au conférencier et après on aura du temps pour discuter.
Okay. Bonjour, good day. So, as Professor Mikulic has presented me, I'm Anatoly Markov from, well, Tecnológico de Monterrey, but from recent I've been working in Skolkovo Institute of Science and Technology in Russia. So, the name of my presentation today is going to be a novel numerical method for the solution of the problems of inhomogeneous cracked media based on a numerical method called Gaussian approximation. So, what's the main objective for today's seminar? Well, it's basically to develop a numerical method and computational algorithms that are capable of solving efficiently two-dimensional problems of elasticity for an infinite inhomogeneous medium containing inhomogeneities of two types, means cracks and inclusions. So, what's the plan of this presentation? First of all, we're going to start with formulating this problem in terms of integral equations, which are boundary for cracks and 3D for inclusions. Then, of course, we're going to propose a numerical method of solution of these equations and some additional post-processing techniques. Mainly, we'll discuss calculation of stress intensity factors for the cracks, and we'll study the problem of crack propagation, crack growth in such media. And of course, we're going to give you some examples of calculations we have done. Let's start with the formulation. We consider some infinite elastic medium that contains some crack with surface omega and boundary gamma. So, according to, for example, the book of Professor Konaun and Levin, the integral equation for the crack surface will be this one, where sigma 0 is the applied stress applied on infinity, the sigma is the stress in the medium, of course, S is the so-called Eshelby tensor, N is the normal to the crack surface, and B is the crack opening vector. Because what happens if we apply some stress to a crack? This crack will open. So a discontinuity will be present and some crack opening would appear here. This is the boundary integral equation which is applied for the crack surface. There shall be the tensor S, which is there shall be tensor, is calculated in this form, where C is the elastic tensor of our infinite medium, and this delta is the Dirac's delta function. This K tensor is calculated through the green function of this medium, which is on each side the solution of this differential equation, where this sigma is the Kronecker delta and L is this tensor, basically. So here we have formulated our problem in terms of integral equations for cracks only. Well, as I have mentioned, if we apply some stress, the crack will open. So from here comes our main boundary conditions, that if the crack will open, well, it becomes a void, so it is logical to suppose that the crack is free of any stress, because, well, it's basically a void now. So the crack surface is stress-free. Then we apply this boundary condition to this integral equation. We multiply both sides on the normal n, and if we know that the crack surface is stress-free, the left-hand side disappears, and we obtain this equation as a result. It should be noted that this integral would formally diverge, because if x would tend to x prime, and it is well, proportional to x minus x prime in minus third. So we would think that it would diverge. But regularization of this integral was proposed by Professor Kanaun in the 80s. So it's not a major issue in our case. This integral may be regularized without any problem. So this is the equation for cracks. Now let us pass to inclusions. By inclusion I mean some inhomogeneity with different elastic properties from our infinite medium, from our matrix. So here we suppose that our matrix has the elastic tensor C0, while our inhomogeneity would have the elastic tensor C1 and occupy some finite region V. So we introduce this function C for the stiffness tensor, well, as a function of V, well, basically. And we propose the following integral equation for the stress field, sigma, which is quite similar to the inclusion for cracks, with the only thing that instead of normal we have this fourth rank tensor B1, which is derived from the not stiffness but compliance tensors of the medium and the inclusion here. So, and of course our infinite, well, the infinite value here is not the crack opening, oh sorry, the unknown value here is not the crack opening but the stress inside our inclusion, is that we don't know. Next step, we suppose that we have a medium with both cracks and inclusion. So simply by superposition of these two integral equations we have obtained, we have this lone integral equation for the whole medium. But of course in the crack case we know that we may multiply this equation by the normal to the crack surface, and for the cracks our point x belongs to the crack surface, we obtain these equations multiplied by the normal to the crack surface. So basically we have this system of two integral equations. The first one is applied for the whole medium except the crack, and the second one is applied to the crack. So how are we going to solve these two integral equations? What's the method of the solution? The method is based on the technique called approximate approximation, which was developed by Vladimir Mazia and Günther Schmidt in their book called Approximate Approximation, which was issued in the 208. So what's the technique? First of all, we take some region of medium of interest that may contain some inclusions or cracks, and we cover it by a regular node grid. Why should be it regular? We're going to discuss it a bit later. So we cover by a regular grid of nodes. It means that this method is mesh free. We don't need any finite elements or boundary. So we only need a grid of nodes, and their geometrical coordinates and normal to the crack surfaces are the only information we need for this node grid. That's it. And the approximation would have the following form. We approximate the stress field as a sum of the values of the stress field in all the nodes of this node grid multiplied by some weight function phi, which is a, well, basically a Gaussian function. We're going to see it soon. And we're going to do the same for the crack opening. We approximate it as the crack opening at the points that lie on the crack surfaces multiplied again by the Gaussian function. So what are phi and c? Again, as I have mentioned, there are three-dimensional and two-dimensional Gaussian functions. So why phi is three-dimensional? Because we have inclusion, it's a three-dimensional problem. But for cracks, as the crack is a planar discontinuity, in this case we may apply a two-dimensional Gaussian function. Phi is calculated over the entire three-dimensional space R here, and psi is calculated over the correct plane P. We may calculate it over the entire space or over the entire plane, because the Gaussian functions are, well, they decrease very quickly. So we may make this assumption that they decrease, they fall down quickly, so we may calculate over the entire space. They fall down, so of course it would cause us some issues, but it facilitates the things a lot. So what is phi? Of course, phi is the three-dimensional Gaussian function. It has this shape, and psi is a two-dimensional Gaussian function. Actually, an example of psi appears here. Well, in the 2D case, it's better known as the Mexican head. Also, so as the country I come from in terms of education. So yeah, this is our Gaussian functions. What happens if we take these approximate solutions and we substitute them into our integral equations? Well, we're going to see it a bit later, but as I have mentioned, there's a problem here with the Gaussian functions. So first of all, let's see some quick example of Gaussian approximation. Well, this is the simplest example of a function that is equal to 1. Let us approximate it with Gaussian functions. So we have this 1, and we take a lot of Gaussian functions. So we take a unidimensional Gaussian function, and we approximate this 1. So this is our Gaussians. The sum of these Gaussians calculated in our nodes should give us 1. But what happens if we zoom in to this 1? We may see that this Gaussian function would oscillate. Our solution would oscillate. Why would it be? This is because there is an error called saturation error, as Mazia called it, that wouldn't disappear. Doesn't matter how much nodes we take, how small we take this step h. H in our case would be the step of our node grid. We would expect that if we tend h to 0, well, the solution would give us, well, the exact result. But despite that, the solution would still present some error called saturation error. How to avoid it? Well, Mazia proposed this factor, that our step of node grid divided by some value L, which is the characteristic dimension of our body, should be bigger than this value, exponential minus pi 2 multiplied by capital H. Capital H here is some parameter of order of unit order, more or less, that this parameter H would define how wide is our Gaussian function. If we take H very, very small, this Gaussian would become very thin. So the sum may present very big oscillation. But if we could take H very, very high, so it would become very, very plain. It's a contrary case that may give us significant error as well. Generally, we consider it equal to 1 or 2, more or less. This is the medium case here. So this is some basic issues with the Gaussian functions. So let's come to the substitution of our solution into the integral equations. So let's come a bit back. So we take these approximate solutions and we substitute them here to these integral equations. As a result, we obtain these two systems of integral equations. The first system is applied for the whole medium except the cracked surfaces, and the second one is applied for the cracked surfaces. So here we have our unknowns, that are the crack opening and the stress field at our nodes. And gamma and I would be some, well, the integrals I have mentioned in the beginning, but these integrals might be calculated without any major problem. So this first integral gamma may be calculated over the entire 3D space R. It was mentioned without any problems. This integral gamma is calculated analytically. It gives us immediate result. About the integral I, we're going to discuss it a bit later. It would present some issues. So anyway, we have a huge system of integral equations. Of course, this system can be solved by normal methods, so we may to apply iterative techniques for the solution of it. Why I have mentioned that the node grid we have applied for the solution should have some uniform shape, because in this case the matrix of this numerical system of numerical equations would have triplet structure. It means that we have only one row and one column to store, and that's it. So we may apply a huge amount of nodes for the same amount of memory. Then, moreover, if this system has triplet structure, well, the matrix of this system has triplet structure, we may apply fast Fourier transform algorithm for calculation of matrix vector products that is required for iterative methods like B-conjugate stabilized gradient or minimum residual. So in these methods we require some matrix vector calculator on each step of the solution. So this method reduces drastically the computational complexity, so it becomes n log n instead of n square for a huge matrix of about thousands of nodes on each side, which it is a very, very big improvement in terms of efficiency of calculation. Okay, yeah. Well, no, the unknowns here would be the the crack opening and the stress field. Sorry? Yeah. Yeah. These are the two unknowns. Yeah. No. Yes. Yeah. Now our unknowns are just the values in the nodes of our grid. Yeah. So. Well. No. No. This is a system of linear equations. Yeah. Yeah. It's just system of linear equations. As a result, our integral equations, yeah, are turned to this system. Yes. So let's talk a bit about these integrals, gamma and I. So as I have mentioned previously, these are some formulas to scare you a bit. But they are to show that this integral gamma is calculated in an analytical form. So we don't require any numerical integration here in order to calculate gamma. It is solved analytically. Well, yeah. Well, yeah. For isotropic, yeah, it's without any issues. Well, the anisotropicity may be modeled by the inclusions, actually. We may model it by this, yeah. Yeah. Actually, there is an example for there, well. But with I, there is an issue. with the integral I, it presents some issue here, because yeah, we may calculate it mostly, but well, then it would be calculated in terms of 5 unidimensional integrals. Actually, I is a 3D. It has 3 integrals. 2 of them might be calculated, but this function integral operator I might be represented as 5 in terms of 5, well, 1D into, yeah, of course. Well, yes, it's simplified, well, and might be presented in terms of 5, well, simple integrals. Well, we may call it f1, f2, f3, and 4, f5. These integrals cannot be calculated analytically. But what can we do with these 5 integrals is that we may find asymptotics of these, well, integrals in this form. For example, for f5, we may propose some asymptotic function, which is polynomial, basically, for, of course, for big values of this integral far from the, well, it's presented in terms of rho, which is the distance from, well, in the crack plane, well, which is the normalized distance in the crack plane from our point of interest, and z is the normalized distance in the, well, in the normal direction to the crack surface. So for far points, we may propose an asymptotic, and for close points, of course, we may just tabulate the values, because let's remember that our node grid is regular. So as a result, we have a very limited number of possible values of distances here. So we may just tabulate these values, and that's it, and store the calculation of these functions. And as a result, the numerical integration is eliminated, in fact, from the solution. So it makes it even more efficient, because we don't need to calculate any integrals in order to construct the, well, the matrix of the system of linear equations. Moreover, we have only one planar crack, which is just plane, belongs to one plane. This integral I is calculated analytically as well, in terms of, well, Bessel functions, second kind Bessel functions, which is even more simple. So that's basically the, well, the basic idea of the solution of this problem. As a result, as we solve it, we obtain the crack opening and the stress field inside some inclusion. Let's see some examples of application of this method. Well, the most basic ones, this first of all, a planar elliptical crack under tension. This is the exact solution given by Irvine, even in the 60s. So this is the normalized exact solution here, and here are our numerical solutions for the crack opening in the x1 axis and in the x2 axis of a planar elliptical crack. Well, it's alright. These are different nodes values for results for different node steps. So, but here you may see some problem, some irregularity in the solution. As I have mentioned previously, we calculate the Gaussian, well, approximation in the whole crack plane. So it means that our weight function has infinite support. And what happens as a result, our solution wouldn't tend to 0 at the crack edge, because we're calculating it in the entire plane. So as you may see, yeah, it tends to 0, but not where it should be. So the main issue of the numerical method is that the values near the edges are not reliable. So we may discard it. Of course, for example, if you're going to calculate the compliance contribution of a crack, it won't be a major issue because we mainly need the crack opening here in this. But for the calculation of the stress intensity factor, yes, it would present an issue. Let us see how to treat it. We need to calculate one of the main, I would say, numerical factor, well, numerical values of that characterizes a crack that is opened is a stress intensity factor, which would, for example, define if a crack would propagate or not. So, in our case, we calculated from the asymptotic behavior of the vector of the crack opening near its crack edge, near the edge, and it's calculated from this asymptotic, which is calculated, of course, on the some normal to some point x0 at the crack edge. So it's basically calculated from the crack opening in a straightforward way. So we need asymptotic. I mean, we calculate this beta, which would be the crack opening divided by the distance from the crack edge, which is s. Let us see how it would look like. It looks like that. We would expect that this asymptotic should go to some infinite value or some finite value, which would give us our stress intensity factor. But of course, because the crack opening is not zero at the crack edge, well, it rockets to infinity, of course. So the most obvious solution here would be to discard this, well, I would say this value, which is we cannot consider for the solution, and just take this value of confidence and extrapolate it to the crack edge. So in this case, well, it would give us a decent result. So it would define the stress intensity factor quite well, as we may see here. This is the convergence of the method, of course, for different node grids. Of course, for smaller node grids with smaller step, well, our crack stress intensity factor on the crack boundary becomes closer to the exact solution, of course. So let us consider another example here of isolated spherical inclusion in a homogeneous medium, which is the solution of Eshelby of the 50s. Here we have the already known solution, and here is our numerical solution of the stress field inside the inclusion and near the inclusion. So it has good convergence in most range, but of course it may present some irregularities on the boundary of the inclusion, but of course it is because of the same reason I have mentioned here. But yes, it has also showed us good convergence for both hard inclusion, which is where inclusion is harder than the matrix, so its Young modulus is bigger, and for soft inclusions with smaller Young modulus as well. So the result is quite alright. These are the basic examples here we have solved in order to prove that the method might be applied for some simple problems. We have also studied some more complex geometries now of interaction of a spherical inclusion in a penny-shaped crack in some infinite medium under some tensile load. We have compared it to some, well, I would say semi-analytical solutions here, and it has also shown us quite good convergence as well with these solutions for, of course, for different geometries. So it was quite alright with very, very small, well, difference. So it was alright. Well, the maximum error here was of, well, 3%, so it was also quite alright here. And we have applied it to a previously unsolved problem. Actually, I haven't seen any solution of a problem of a crack intersecting with a spherical inclusion. We have also solved it. And calculate the stress intensity factor on this penny-shaped crack edge. Here it is the stress intensity factor here. So it was a previously unsolved problem. So in order to prove the flexibility of the method, that it might be applied to some unsolved problems as well. And the most recent development of this method was the calculation of the equilibrium crack shape. But under equilibrium crack shape, we understand the crack which stress intensity factor on the edge of which crack is equal to the fracture toughness of the medium. So it's the biggest crack that will propagate. So we calculate it by some simple iterative procedure. So it means that, for example, in simple words, if stress intensity factor is smaller than the fracture toughness, we should grow the crack a bit so it would coincide it, and vice versa. So we calculate the equilibrium shape by this technique. Well, in simple words of this. And we stop, of course, when the stress intensity factor is more or less equal to the fracture toughness. Why is it necessary? This calculation is basically the base of numerical simulation of hydraulic fracture growth, which was a project developed recently with Professor Canaun, in Mexico. So this calculation was the numerical base of this calculation. Here's an example of how we calculate this equilibrium crack. We start from a penny shape here at the moment 1, and slowly it goes to, this equilibrium shape here in this medium. For x2 smaller than 20, the fracture toughness is equal to 1 value, and from x2 bigger than 20, it has a different, bigger value. So the equilibrium crack shape would be this one. Of course, if the fracture toughness is bigger, we would expect that the crack wouldn't propagate that much in that direction. So for x2, for more stiff, we would expect this, that the crack wouldn't propagate that much. Actually, there's an error here. I haven't noted this. Here it should be bigger, of course, because the fracture toughness, for bigger fracture toughness, the crack should propagate less. So yeah, here you calculate this equilibrium crack shape. Let us consider this example, which is a crack under logarithmic pressure, which is basically a simulation of hydraulic fracture. That is called a 3-parametric hydraulic fracture model, which was published recently in the work of Canaun, and this one in the last year. So we simulate the hydraulic fracture, the pressure of the liquid, as a logarithmic one. So, and first of all, it should satisfy the Poiseuille equation and of course the flow equilibrium and at each step, because the hydraulic fracture growth is basically quasi-static. So we simulate step by step, and at each step the stress intensity factor on the crack boundary should be equal to the fracture toughness, as I have mentioned previously. So this is what we should calculate by this numerical solution for, each value of the pressure, which is found from these two equations. That was the goal of application of this numerical technique, basically. So we have to calculate this crack shape for this pressure, which is logarithmic. So here is an example of the crack growths. Again, for x bigger than 20, we have a more stiff medium with higher fracture toughness, so we would expect that our crack wouldn't propagate there that much, and here of course we may see that it propagates on the other side, of course, which is softer in this case. This is the same medium. We have also considered a medium which were not also the fracture toughness, but the Young modulus of this layer is proportional. So the dotted line corresponds to this case, where not only the fracture toughness, but the Young modulus of the medium is also variable. So actually in this case it was closer to penny-shaped, which is a very peculiar result. But if we have found that if the both fracture toughness and the Young modulus are proportional, the crack is close to penny-shaped. The equilibrium crack shape becomes close to penny-shaped. But in the case we leave only fracture toughness variable, yes, it would have a irregular shape, which was a very interesting result here. So this is one example, and this is our crack opening here, as you may see, for this the same crack, well, equilibrium crack shapes that are shown here. This is the crack opening. We have also applied it to a more, I would say, a more real case, because in the case of fracking we would expect this our injection point to be well, here we have a layer with where our gas or where the fracking is applied, but generally it is situated between two more hard layers. So we have an example of fracture growth between two hard layers, and the medium layer is a soft one, but it has shown us a very similar behavior, this modeling. So of course we would expect that the crack grows more in a more soft medium. But of course the irregularity is quite smaller, because the crack is, well, restricted by these two hard layers. So this is another example. And again here we have the crack opening, just in case. Well, it has this form. Of course, because the pressure is logarithmic, you would expect that the crack opening would be bigger in the injection point here. So here are these examples I have given you. So let's pass to the conclusion that the method developed combines the Gaussian approximation used for the solution of problems of cracks and elastic inclusions in the infinite elastic medium. So we may simulate some anisotropic media, as we have seen. For example, we have applied it to a layered medium, where the layers were simulated as inclusions, and also to finite inclusions as well. We may simulate both of them. The huge advantage of this method is that the Gaussian approximation allows us to get rid of numerical integration at all, so it improves the efficiency. And of course, for example, for this hydraulic fracture simulation, we need to solve this problem a lot of times, and it is huge advantage. The method is mesh free, which is, it belongs to this branch of numerical methods. The matrix of the discretized system would have the triplet structure, which is the obvious advantage. This method might be applied to planar cracks and inclusions of arbitrary shapes, so it doesn't matter. All the shape is basically defined by just by some index function, and that's it. So we don't need to draw it somewhere in CAD and import the geometry. This is actually not necessary. Well, the cracks and inclusions are simulated by just an index function, and that's it. The stress intensity factors are calculated by this method in a simple form. This method would allow us much larger number of nodes because of the triplet structure. So then we have proposed an iterative method of equilibrium crack shape calculation, which is basically essential for quasi-static, let's say, simulation of crack growths, as the crack grows under some pressure. And this method was applied to a hydraulic fracture process simulation. So, and we need this calculation. And again, it's possible to apply the method to solve some different problems involving integral equation with only minor changes. It was applied by Dr. Kanaun for the solution of conductivity problems for thermal or electric. Actually, it's the same equation, so was applied to some problems of poroelasticity by Professors Kanaun and Levin. Now we are applying it to, I hope we apply to some it was applied for homogenization previously, and actually I think I'm going to apply it now in School Tech. So with the range of the problems to which it might be applied is huge, we would say. So this is the bibliography of the works that were mentioned, and thank you for attention. Merci pour votre attention. Thank you very much.
Very nice presentation, and you could really good see how analytical methods are fertilizing each other, so to say, and so maybe there are some the first one is the case of anisotropy.
Yeah. Yes. Yeah. It wouldn't be as nice. Yeah. Yeah.
My concern is I don't see what is the advantage of your method with respect to other integral equation methods. For example, discontinuity displacement methods are very well known methods, integral equation methods, but there is no limit to use this integral equation. So my question is the cost of the computation, the accuracy, what is the advantage of your method? I understand that is method.
Yeah.
But I don't see the advantage comparatively to other integral equations.
Well, actually, I'm not quite familiar with the method you have mentioned. So, but as I I know, of course, yeah, I know, yeah, but yeah, well, yes, yeah, the main actually, actually, I think that in terms of, if you're talking about the the calculation of these integrals, the main advantage is the application of Gaussian functions, because, basically by their essence of the Gaussian functions, which is exponential, here, because by the essence of Gaussian function, it simplifies a lot the calculation of any integral or differential operators, because there's an exponent, so it yeah. Yes, of course. Yeah. Yes. Yeah. 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 Yes. Actually, yeah, I understand your question very well. Actually, there is work planned on this issue. We are planning, well, to perform some, well, experimental calculations in order to compare it to some, for example, for instance, some commercial software that is also, well, present on the market. For example, even with the finite element software, yeah, we're planning to perform some experiments on this issue you have mentioned. So yeah, to prove the, well, all the mentioned advantages of fast integral calculation and of the possibility to consider a lot of nodes. Actually, well, I have considered several millions of nodes. It wasn't a problem for, and they occupied only some, well, an abysmal amount of memory. So yeah, but yes, we're planning to perform an experiment on this issue. Yes, it's a very good question. Yeah, I understand it. Yeah, it is planned.
What about
semi-infinite? Well, it of course, it would depend on what do we need to calculate, but probably. Well, we may. It would be probably a bit difficult because our integral equation is a boundary integral equation here. So probably, yeah. Yeah, of course. Yeah. Yeah. But probably we'll have to introduce some boundary condition, fictitious one. Actually, for this method, we don't need, for example, if you have a homogenization problem, calculate, well, some homogenization, calculated by this method, we don't need any boundary condition at all for our RVE, representative volume element here. But this is a finite problem, of course, of finite volumes, of finite cracks. For a semi-infinite crack, yeah, probably it would present some issues. We would need to introduce some fictitious boundary conditions, because of course we cannot simulate it in a straightforward way in this case. Yes, we could simulate an infinite layer, because, well, if we take it a sufficiently large volume, and we are calculating, well, our geometry of interest is the crack. So yes, as you have seen, we could simulate it. But for a semi-infinite crack, yeah, it would be, yeah. I think it's possible, but it would present some issues, I think, yeah.
The other question is more related to one of the main physical results you present us, that stiffer material, increasing Young modulus, seems to prevent propagation.
Yes.
The crack doesn't go as much as it goes for softer. It's not that straightforward. Do you have interpretation for that?
Well, actually, I think this is as well. It should be studied quite well, but I think the problem is that, for example, as we calculate our stress intensity factor from the crack opening. So, if you consider a high Young modulus, for example, as here for the
crack is shorter.
Well, of course, we would expect that the crack wouldn't open that much, so the stress intensity factor would decrease as well. Here, I think this is the reason here. Actually, if you take a look at the time here, of course, the crack propagates much slower here. Yes, but I think the reason that its shape is closer to penny shape is because of that. Because I mean that higher Young modulus means smaller crack opening. Smaller crack opening would mean smaller stress density factor. Calculation, yeah, I think. But of course, as you may take a look at the time, of course, it propagates much slower. It propagates less. In the case of, if you consider this, well, to have space to have a high Young modulus. So of course it propagates less.
It's not. It's not. Yeah, it's not an easy question. I think you may think in terms of G also. G, elastic energy release rate, but it's probably the right quantity, is in 1/E. It's a possibility. Okay. I'm not sure. It's could be checked.
Yeah, of course. The proportional, yeah. But yes. Okay.
Symmetry properties such as rotational symmetry, then you can evaluate these integrals in closed forms. Then it may be your method best useful. Is it true that one can say your method is for this kind of problem class maybe?
Well, in I'm sorry, in mechanical no, actually the main advantage of this method is that it might be applied to arbitrary shapes, as I see. So it might be applied to not to some symmetric shapes. So we may take crack of any shape, like here, for example. It is irregular.
The problem, the selection of the basis set, because of this age, you mentioned that when you have, for instance, one, then you would choose age very large. Then
okay. Yeah.
That your basis set is somehow incomplete, and maybe you maybe this kind of replace. You can on the one hand well integrate the terms, but you are not sure choosing the right basis set.
Okay. Okay. Well, the capital H is actually it's a parameter to play with. Actually, yes, it's not defined strictly. Well, the only definition is this. In inequality. Well, actually it's generally 2. Well, it works for most cases. Yes. Well, we may play with it, but generally we use it at 2. Yeah. Yes. So basically it's just parameter to fit. So it's not quite an issue. No, it's actually yes. From the British point of view, the crack stocks cannot go through the interface between the two. So the only solution is the crack succeeding going through, which means that it jumps. Yes. If you are examining basic solutions, the crack stops. Yeah. Yes. Yeah. So there is no crack, doesn't have to cross. Yes. Yeah. Okay, yes. No, actually you're right. Yeah. Actually you're right. Actually here I have considered this example because of, well, in order for it to be representative, I mean. But actually if we zoom in to this area, actually in a recent work, well, I had how it grows. So for a while it would be it would be have this shape more or less. So it wouldn't cross the boundary actually for a while. So it would grow, or for example here, it would have this shape. It would be almost straight here, and then it has this shape. So yes, it won't cross the boundary for a while, even in this quasi-static approximation. But yes, then it jumps. Yes. Yes. Yeah. Okay. One moment. I think I. Yeah, actually, okay. Yeah, actually, sorry. These are recent work, so yeah, here we have these boundaries. It is a more recent picture here. So yes, for a while it would propagate this way. So it wouldn't pass the boundary here. But then, yeah, it jumps over it. Yeah, this is a more recent picture of this crack growth. So yeah, it's a very good question, but yes, for a while it would propagate only to the sides of a soft material. Yes, that's right.
If your method is not meshless, I will not ask this question.
Yeah.
Because it seems that it can be an advantage. Because some people make some attempt to extend the integral equation in order to incorporate plasticity also. Okay, and in fact, this has not met success, and people now stop to try to couple plasticity with elasticity in the case of integral equation. But your method is meshless. So my question is, do you think that is possible to do something to integrate non-linearity, plasticity or something like that, due to the fact that you...
Well, this is a very good question. Well, the only thing I can say that we may try to do it. But actually, until now we haven't touched this area.
People who want to extend this consider that the plastic zone is something with angle strain. Okay.
Yes.
Plasticity definition is interpreted as angle strain, but they are obliged to
of course. Yeah.
For that reason.
Yes. Well. Yeah, I imagine. But yes, it would be a very interesting, I would say, addition to this method, because, well, yeah, it's integration is simple, but yeah, it would be quite.
Thank you very much for your very nice
Okay,
talk again, and
thank you. Thank you very much.